is this one, and this one basically is corresponding to parabolic or hyperbolic orbit. Okay. Sorry, the only hyperbolic orbit. Q equal to 1 is parabolic. Okay. So now for this case, and again, if we only talk about the parameters, a little bit complicated. So let me do the examples, and from the example we can be much easier to understand. So say, for example, if we say consider the QBO equal to 1.2, okay, and given the R and V, and we have the VBO equal to 1.2, then we see what happened. So we plug in here the VBO plus VFF over 2 equal to, plugging the 1.2 here basically is become 2 over 3 and sine VFF over 2. Okay, so again for this case we want to know the flight path angle, and we want to know the say flight path angle and flight range angle here. So under these situations, then you can see for this case is always less than 1. This is always. Why is always? Because sine, this value is, the maximum value is 1. And 1 multiplied with this coefficient, so it's always less than 1. Okay? So if the case is always less than 1, then we see so to solve for, so therefore VBO, let me do step by step. So plus VF over 2, basically equal to arc sine of 2/3 and sine VF over 2. Okay, because this value is less than 1, so let me say again, on the left hand side, that is a sine functions, and let me say these are sine functions, and then this one, let me say this is the 2 VBO plus VFF over 2. Okay, so for this case, we know the sine of this one is less than 1, so we have 2 values here, and one solution is arc sine, and of this number 2, 3, and sine VFF over 2, so that is this number here. And the other numbers is pi minus the same numbers here. Okay, so here we have 2 possible solutions. So here, or pi minus okay, good? Okay, then we can solve for VBO. 2 values, and you can just plug in. Okay, so here is 1/2 sine, let me write it again, minus, or so that is the situations we might have. So again, in this way, the function, the VBO, is determined by the flight range angles. So here we see how the functions look like. So similar to case 1, Q is less than 1. Here I want to draw the functions. Okay, this equation provides a relation between the V and psi. So it's easy for us to draw it. So here, let me do this way. So here is a value of 0. Okay, and here is the value of pi and 2 pi, and I simply use MATLAB, and and then I do the calculation. I given a value of psi, and I given a value of psi, so that means on the right hand side I have the calculated numbers. So here I have two values of VBO, then I draw the two curves. The curve is this. Okay, the curve will be look like this. Okay, and you can play around and for different Q, but by changing the Q greater than 1, the trend of the two curves will be look like this. So that means one value is always positive, the other value is always negative, and which value is which value. And here, let me say this is the larger one. So this is VBO2. So let me say this is VBO2. Okay, and the VBO1. This is VBO1. Okay, so one value is always negative. And again, the negative one won't be practical, and depends on the situations. Okay, so here I leave that for you to justify. So again, for you to pick the right angle, you have to avoid any trajectory that can dig into the earth, and that is not practical. Okay, and to do that one, that can be easily checked once you draw the curve, say if this is the earth. Okay, so say for example, say if you want to choose this is a burnout. So say if you want to choose the psi equal to pi, so that means this is our re-entry. Okay, so under these situations, you shouldn't choose this one because that is negative value. You have to choose this one. So that means if this is the lower horizon, then this will be the V. This is the V, VO, and the value positive is 2. Under these situations, that will bring you, and on the hyperbolic orbit, this is a portion of the hyperbolic orbit will bring you to here. Okay, and most of the designs the people making is not this case, is for Q or less than 1, because that is taking the less fuel. Okay, the size of the rocket is determining the amount of the fuel determines the size of the rocket, and they're always looking for the optimal design, which corresponding most of the time is Q less than 1. Okay, so more practical situation is our case 1, and that reason I spend more time on the case 1. Okay, so that's it.